Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. While at the NIPS conference back in December, I attended the Black in AI workshop and dinner and had a chance to meet a bunch of amazing people. This week on the show, we'll be highlighting some of the great work being done by folks in this community. In this episode, I'm joined by Moustapha Cisse, research scientist at Facebook AI Research Lab, or FAIR, in Paris. Moustapha's broad research interests include the security and safety of AI systems, and we spend some time discussing his work on adversarial examples and systems that are robust to adversarial attacks. More broadly, we discuss the role of bias in datasets and explore his vision for models that can identify these biases and adjust the way they train themselves in order to avoid taking them on. Before we dive in, we want to hear about your experiences with home and personal AI. So we launched the My AI video contest last week. Please head on over to twimlai.com/myai and take a few minutes to submit your thoughts on the role AI is playing in your home and personal life, your favorite example of home or personal AI, the AI that you really want to see in your lifetime, or just where you see this all going. The entries with the most likes will win great prizes, including a Cosmo and a Lighthouse, both of which we discussed on our AI in Consumer Electronics series last week. And now, on to the show. All right, everyone, I am on the line with Moustapha Cisse. Moustapha is a research scientist at Facebook AI Research Lab, and we had the pleasure of meeting at the recent NIPS event. And particularly, we hung out quite a bit at the Black in AI, both the workshop and the dinner. Moustapha, it is great to reconnect with you. How are you doing?
I'm great. How about you?
Fantastic. So the tradition here is for me to give you an opportunity to introduce yourself to the audience. So why don't you tell us a little bit about your background and how you got interested in AI?
Sure. So I'm Mustafa. I was born and raised in Senegal in West Africa. If you have never been there, you should. It's a fantastic country. Just a little bit of ad.
Nice.
So I was born and raised there, and I did most of my education there. I went to the University Gaston Berger, where I studied mathematics and physics. And it's during one of these courses that I really got interested into AI. It was an algorithmic course where we had a project. The task was to design an AI basically to solve the game of Awale, which is a strategic game, a bit like checkers or chess, but very popular in West Africa. And most of the systems that were designed by the students were based on rule base, like if you do if then else rules, basically. So I really wanted to design a system that learned from different games and learns to solve the game, basically. So that's how I got into AI. So I started watching videos on YouTube and teaching myself some of the basic algorithms.
Okay, awesome. And so how did you make your way from there to your current role at Facebook AI Research?
So after that experience, I really enjoyed it, and I kind of realized that this was what I wanted to do for the rest of my life. I could contribute in this area. So I decided to go abroad because there were not an advanced course or degree in AI in the university. So I went to France to study for a master's. Okay. So I studied. I spent the first year in Paris at the University Pierre and Marie Curie. Then I spent the second year at the University of Montreal. Then I came back to Paris to do a PhD there. And then after I graduated from my PhD, I did a 1-year postdoc. And after that postdoc, I came to Facebook AI Research. So it's been.
And you're based in New York City, is that right?
Actually, I'm based in Paris, even though I spend some time in New York sometimes.
Oh, okay.
Yeah, but I'm based in Paris. So we have a lab in Paris, with about 30 researchers and engineers.
Oh, nice.
Yeah.
Nice. And so maybe we can start out by having you tell us a little bit about your research interests and the kind of things you're working on nowadays.
Yeah, so I'm interested in AI, in machine learning at large, but these days I spend most of my time working on trust in AI. So by trust, I mean all the topics pertaining to safety and security in AI, fairness and biases, and also interpretability. I think these are very important topics that are gaining some momentum now, but that have been overlooked for some time. And it's very important that as a community, we focus on building systems that can be trusted and that can be used uh, broadly, to say.
Mm-hmm.
So that's what I spend most of my time working on right now.
Okay. Can you maybe give me some examples of recent research you've done in these areas?
Sure. So in the area of security and safety, I have worked on understanding the topic of adversarial examples. So adversarial examples are examples that a model, so an AI system, sees or hears, or depending on the modality, but that makes the model behave in a completely different way that it should behave. That is in a completely unexpected way. So these are malicious examples, and they tell us a lot about how the models that we are building right now are kind of not very well understood. So I have done some work with colleagues in understanding how these adversarial examples arise and how to generate them for speech recognition or for semantic segmentation, which are very challenging tasks, but which have applications in personal assistance or in self-driving cars. And it's very important to be able to create these adversarial examples, because that's the first step in order to evaluate the robustness of an AI. So then we moved on working on defenses against these adversarial examples. We have also done some work in this area, which have been recently published with some colleagues here. And another line of work is also this area of biases and fairness. So recently we have shown in a study that the models, basically the deep learning models that you use to recognize images when you train them on a popular benchmark dataset, which is ImageNet, they learn quite some biased decision-making process. And this is somehow unexpected because most of the time the data set is considered as balanced. But there are explanations for this. So we have observed some interesting biases, ranging from racial biases, for example. And all this is described in the paper.
Okay. I think I've talked about adversarial examples in my newsletter, but I don't think we've really dug into it in the podcast, at least not in a lot of detail. So maybe let's start there. And for folks who aren't familiar with that whole field, do you have some favorite examples of adversarial examples?
Sure. So imagine you have you have a system that is supposed to tell you what is in a picture. So if you present the system with a picture, it says, "Oh, this is a dog, or this is a cat, etc."
Right.
So it is possible to inject to the picture that you're presenting to the image some very structured noise that is imperceptible to the human eye, but that will change the decision of the system. So you can have two seemingly identical pictures of the same dog, and for one of them, the system will say, this is a dog, and for the second one, the system will say, this is a cat, or this is a car, or any other thing. So this is kind of intriguing because these systems are very accurate normally, and we tend to compare them to humans because they are very accurate. And when we measure their accuracy, we say, hey, look, the system is as accurate as a human. But on the flip side, a human is very robust to these kind of perturbations. Like no matter how much perturbation you add to an example, if a human looks at two pictures that are similar, she will be able to say that this is a dog and this is a dog as well. But if the system can be tricked by these slight modifications that are imperceptible to the human eyes, it means something. It says a lot about the current understanding or the lack of understanding that we have about the behavior of these models, and it makes it an interesting topic to study. So this is basically the a high level explanation of adversarial examples. By the way, I gave an example speaking about topics on speaking about images, image recognition, but.
And I think that's what most of us associate with adversarial examples.
Exactly.
We've seen a bunch of these.
Yeah.
But it's not just images.
Absolutely. So we have shown in a recent paper a generic method called Houdini that allows you to generate adversarial examples, not only for images, but also for speech recognition tasks, where you can add some noise in an audio file such that humans cannot distinguish the two audio files, but a speech recognition system will interpret the two audio files in a completely different way. So it's a very broad topic.
Oh, wow. So, the example that comes to mind for me is if you can create an audio file that says one thing, but interprets the system as saying, "Okay, Google," you could really mess with people's their virtual assistants and things like that they've got around their home.
Sure, that's one scenario you could imagine. Definitely, that's one scenario you could imagine.
To what extent are the current adversarial examples that work in general? Like, to what extent is that model specific? Meaning, is the work that's happening around adversarial examples and defenses, is it all explicitly impact specific types of models, deep neural networks, or specific types of deep neural networks, or specific architectures of networks, or is it a broader phenomenon that can apply more generally?
So I would say that this is a broad phenomenon that applies to different class of models, ranging from deep neural networks, of course. People talk about it because it's the most familiar family of functions right now, but it also applies to support vector machines or to decision trees and all sort of things. That being said, the kind of model the specific type of model that you're using can have properties that make it less robust to adversarial examples. This is true across the different family of models, but depending on the conditioning and the some nice properties that the model may have, they may be more or less robust to adversarial examples. However, for the defenses, there are defenses that exploit the nature of the model sometimes, but there are also some defenses that are agnostic to the type of model that you consider. For example, we recently proposed in a paper defenses against adversarial examples that are just based on transformations of the input in order to remove the noise that has been injected to the input. So this is typically completely agnostic to the type of model that you consider.
Okay. When these adversarial examples, they're maliciously created, what's the process generally for creating them?
So the process for creating an adversarial example is actually the inverse process for training the model. So when you train the model, you show to the model an image of a dog, and you measure how well the model recognizes that this is a dog, and you reinforce that decision if it is a positive one, or you kind of encourage the model to change its decision if the decision is not good, right?
Okay.
So when you create an adversarial example, you do the reverse process. And the way you do it is that we show an example of a dog to the model, and when the model says, yes, this is a dog, then you calculate from the model the right direction in which you need to move the example in the input space in order to change slowly the decision of the model, which means that you're based on the decision of the model in order to know how to trick it. So it's the opposite way of training the model. So the subtlety here is that changing the decision of the model does not require a big change in the input space. In fact, if you consider images at the pixel level, that change is always almost imperceptible by a human eye. But it is surprisingly sufficient for flipping the decision of a model.
There are technologies in the case of images and audio as well, where you can have like these digital watermarks where you're doing similar things, right? You're placing some kind of watermark. I guess in that case, it's not noise per se, but you're altering the image in a way that's imperceptible to the human observer, but has some meaning to the system. I guess I'm just sharing that as kind of an example of how
it's
that
actually very
process.
Related. It's really it's very similar. It's not the same thing, but it's very similar. That you manage to put in the input some information that makes the model behave in some way, but that is basically imperceptible. And you're definitely right, pointing to the watermarks, because it's very similar in spirit.
And so there are a bunch of folks that are researching these adversarial examples. What's the current research thrust? Is it trying to identify different ways of generating them, or have we all kind of, is there, only, that general way that you described to create them and everyone is working on defense, or what?
So there are different rules for generating adversarial examples, but they basically exploit the same information, which is the gradient. In one way or another, it can be direct when you have access to the full information about the model, or it can be direct where you kind of train a substitute of a model and generate the gradient from it and transfer the adversarial example to another model. So there are a few different attacks that do exist, but for now I have to say that attackers have an edge, because it's much more difficult to fool a model than to protect it from adversarial examples. However, in my opinion, adversarial examples are not just interesting from a security point of view. Of course, this is very important because it's critical when you want to use these powerful and attractive deep learning models, for example, in certain types of applications. But another aspect of the adversarial example is that they tell us something about the models that we love and that we use on a daily basis. They say that there are things that we do not understand because this behavior is sort of pathological. So they trigger interesting research questions beyond the security perspective, but on the very nature of these models and the learning algorithms that we use. And we have also found with other colleagues that adversarial examples can be used for other purposes. And in our case, it was to exhibit biases that the model may have learned from the data, which was quite interesting to see.
Can you elaborate on that and what the implications are?
When you have a model, so basically machine learning models, or you design a parametric model, you take some data, you apply a learning rule, and you train the model from the data, right? So you can expect that if your model is trained to optimize for some criteria, it will behave very well if the learning algorithm is good, if you have sufficient data, if the model that you have chosen is powerful enough that it will behave in some expected way, right? But
assuming your input data is, follows a similar distribution.
Absolutely, that's the PAC hypothesis. Very good observation. So the point here is that your model may have captured some regularities that are present in the data, but you may not notice, because when you test the model or when you evaluate it, you're not using the right criteria that could show you the broad scope of everything your model have learned. So
Okay.
I can give you an example. So we have found that, for example, if you take let's say popular models like ResNets, residual networks, which are very popular in computer vision, and you train them on ImageNet using all the sophisticated learning algorithms, then you will achieve some excellent performance as far as accuracy is concerned. But when you look deeply into why the model predicts what it predicts, you can see some very funny things. So, for example, we found out that if you consider the category basketball, so for some reason, the model tends to consider that if you show an input with a black person to the model, it will predict that this is a picture whose corresponding category is basketball. And this is no matter whether it is about basketball or not, doesn't matter. And the reason is the model has picked up some biases in the data. So that suggests this actually, and it's true also for different sort of biases.
It almost makes me think that like all models overfit. It's just some of them overfit too much, but the other ones are overfitting in ways that might produce acceptable results until we're thrown a curveball and see something that we didn't expect.
Absolutely. This is a very good observation. So many of the models, if they are not properly regularized, or if the loss function, the objective, the criteria that you're optimizing for, does not take into account these problems, they may well learn a different sort of biases from the data. And these biases are numerous and diverse, by the way. So I always put it this way. I think you are what you eat. And for models, the data sets they're trained on right now are just junk food. So we should not expect them to behave differently if we don't endow the models with the ability to pick precisely the examples they should learn from, and what they should learn and what they should not learn. Just the way we do it with the kids, for example. When a kid takes something and put it in her mouth, if it is something that a kid can eat, you probably can let her do. But if it is not, then you will stop her and say, "Hey, you cannot do this." And as adults as well, sometimes we say, "Oh, I can eat this, I cannot eat that, because there is a lot of fat here, there is not enough, there is a lot of sugar here, etc., etc." So we should endow the models with the ability to do some self-criticism and introspection, to say, I should learn from this data set, I should learn from this data point, or I should not learn from this data point, etc., etc. So these are very fascinating questions I spend a lot of time thinking and working on these days.
So I wanted to drill down into that last point you made about endowing the model with this ability to kind of discriminate between good and bad data. But before we do that, we kind of got to the bias by way of the adversarial examples. And I think you were making a connection there that I didn't fully catch. And I want to make sure that if that is what you were trying to do, that we make that clear.
Yeah, sure. So the reason why adversarial examples can be interesting to exhibit the biases a model may have learned is actually very simple. So when you learn a classifier, basically what you're trying to do is to find a decision boundary, to draw a line that says that this side of the line, it's the cats, and the other side of the line, it's the dogs. This is very simple, and you can visualize it very well if the model is linear. But if the model is non-linear, it's much more challenging. And the way adversarial examples are built, it's by taking a point of a specific class and moving it slowly, but in a very straightforward way, to the other side of the decision boundary. Right. So not all examples are created equal. If an example is close to the decision boundary in the latent space, then you will not need to move it a lot in order to take it to the other side of the decision boundary.
Mm-hmm.
And if an example is far from the decision boundary, you will have a hard time taking it to the decision boundary, to the other side of it, meaning that you will have to add a lot of noise, a significant amount of noise. But the examples that are close to the decision boundary are those examples for which the model have learned a representation that is not very robust when you consider the concept they should belong to. So if you take a picture of a dog and for which you can flip the decision of the model very easily by adding very small amount of noise, that means that the model is not very sure about what this is. And that is called a criticism. So this is a criticism for the model. It's something that the model barely knows what it is, but it's not very sure. But if you take a picture of a dog and you add a lot of noise to it and still you have a hard time flipping the decision of the model, then the model is pretty confident what this is, right? So, and that is what the model considers as being prototypical. So after learning from some data, you can take another data set, some test data set, and by using the procedure for generating adversarial examples, you can see how much noise you should add to some data points in order to change the decision of the classifier, and use that as a proxy of how prototypical an example is to the model. So the examples that are prototypical to the model, to what the model have learned about a given concept, will be hard to change their decision. But for the others, it will be easy to change their decision. And if you look at the prototypical example, they will tell you what the model has really learned, what it is very confident about. And that's actually what we used, and in order to discover what the model considered really as being pictures of basketball. And when we looked at it, it was all pictures of basketball, basically with just black persons inside and never white persons. And when we looked at pictures of that are criticisms, which is, some pictures that the model classifies pretty well, but it's not very sure about it, it's at the edge of its knowledge, then it's pictures that are mostly populated with white persons. And all this is basically validated on different categories and different classes. Similarly, we found that when the model, what the model considers as being prototypical of an image belonging to the category ping pong, is basically a picture with an Asian in it. So after, when people see these kind of things, they will say, hey, the model is racist. In fact, a model cannot be racist because it's not intelligent. The models that we build are accurate, but they are not intelligent. And whatever they learn, whatever behavior they exhibit, they just learned it from the data they were trained on. So somehow these models are the mirror of what we are. So they just tell us something about the process we use to collect the data to train the model. And sometimes they even tell us something about those who collected that data and those who built the model. So I will take this occasion to emphasize on something that is very important regarding diversity in our community. It's actually critical, and not just because it's fashionable or because it sounds cool. It's critical that as a community we become more open and more diverse, because the models that we build and the data sets these models learn from, if we want to have a broad impact at the global level worldwide and build technology that is representative of the human beings on this planet and not just a specific population, which tends to be Westerns and North Americans, it's important that we become more open and more diverse so that everybody has the tools and the techniques to build the technology to solve its own problems.
Well, everyone has the tools and techniques, but also those organizations that are building, these types of systems, have a more natural inclination to structure their data sets, for example, so that they're more robust.
Actually, I'm not even sure that everybody has the tools and techniques, because let's say let's consider the machine learning community, for example.
Mm-hmm.
So this community every year organizes conferences, which the two of the most important ones being NIPS and ICML. And they are basically every year organized in a Western country, either in Europe or in the US, with some exceptions. ICML has been organized previously in China, for example, and last year in Australia, which I consider being a Western country as well. And it is very difficult for people from other parts of the world to get into the community, just because the places where these gatherings happen are not easily accessible to them, and that's one thing.
Right.
That's one thing. And when you are European or American, you may not see these things because you have the right passport that allows you to go everywhere. But when you are not, then you can see this. I just give you an example. This year, I had 2 papers accepted for publication at ICML. It was in Australia. I could not go there because they did not grant me a visa.
Oh, wow.
For many people, this is they don't even believe it when you say it, but it's true, and it's just like the normal, the routine for many people. So that's one thing, and the second thing is that even for those who manage to attend these conferences, if they're not established in a lab that is in one of these countries, it can be very difficult to do some research, some interesting and important research, because most of what we do right now requires huge amount of computational resources which are not available in many countries. So we need to do something. So there are various initiatives to make the community more open and more inclusive. Some of which I can name are the Women in Machine Learning, and also the Black in AI, which we organized this year. We also have this initiative called Data Science Africa, which we organize every year. It's a summer school where we teach machine learning to local students, which has been very popular so far. So there are initiatives, but I think we need much more.
I'll also throw in a shout out to the Deep Learning Indaba, which happened in South Africa for the first time last year. Yes. And they're planning a follow on this year as well.
Yes. That also is an interesting initiative that was very helpful in this direction as well.
Interesting. So, and I guess in that way, all of the, I think that kind of ties together all of the various things that you work on that may seem like separate and distinct areas of research.
They're not really separate. They fit in what I think as a person I should be doing. So I'm committed to build an axiological artificial intelligence. And by axiological, I mean an artificial intelligence that is aligned with the value of the society in which it operates. And to be aligned with the value of the society in which you operate means that you are aware of the biases that you should avoid, but also you are aware of the utility that you can have, the problems that you may solve, and also the guarantee some level of safety and security. So that's the general scope of what keeps me busy right now.
Which brings us back to that previous comment that I kind of put a bookmarker on, and that was kind of the distinction you made between us as the creators of the AI being aware of bias in data sets and factors like that versus the models themselves being aware of these things and evolving through training or design or other things to, I guess the way you put it was be selective about the data they consume. Can you elaborate on that and the kind of work you're seeing happen there?
So what I said is that you are what you eat, and the data the models are trained on right now is basically junk food. So what I meant is that we do not put a lot of effort into ourselves first, looking into this data and seeing what the model what should be there and what should not be there. So, for example, if you collect the data that serves to train a model which will be used worldwide, then you make sure that that data is representative of the population worldwide. That's the basic first step to do.
I get that part. I thought you also, and maybe this is where you're getting with the second step, I thought you were also suggesting that you're also exploring ways to teach the model to know these things.
That's where I'm coming. So so the first part is the data part itself. Actually, there is the degree 0, which even comes from before the data part. The zero step 0 is to make sure that the people who work on the data and on the model are as diverse as possible, because only that way they will be able to notice these biases. And of course, the first step after that is to make sure that the data itself is representative of the population. But then after that, which a little bit more technical question, is the models should be endowed with the ability to select what they should learn from and what they should not learn from, and what kind of features they should be invariant of. And this is a less explored territory, because there is definitely some work in the area of making the models invariant to gender or invariant to race, etc. But I think we should, in order to design models that are intelligent but that are free from the biases, we should just take inspiration from ourselves. We humans do some do introspection. Basically, when we see a book and we read the book, we don't believe everything in the book, right? We say, "Oh, this makes sense. This doesn't make sense." We criticize many of the things, and that's also part of learning. But right now, that learning is completely positively supervised, which means that when you show an example to a model, the label it is associated with is exactly what you want to learn from. So we should endow the model to be able to criticize the data it is learning from, and to select what it should learn from according to some criteria, and what it should not learn from according to other criteria. And to me, this is an exciting direction, research direction, which has not been much explored, I have to say, but it's something that we should work more on.
Are there any examples of this, even very simple ones that have been explored in the research?
So recently I published a paper with a colleague of mine where we tried to do something like this. We try to, but for a model that is already learned, we try to design a method that allows an operator to take the model and apply the algorithm in order to exhibit the biases of that the biases that have been learned by the model. But then one could imagine that this algorithm is applied recursively to the model while the model is being trained, and that's where it gets interesting.
Almost like a GAN type of training approach?
Something like that. Not necessarily a GAN, because in this way it's I don't see it really as being invariant to something, but really as being able to criticize itself, and also to decide which data it should learn from and which one it should not learn from. So more in an active learning fashion, but it's a bit more complicated than that.
Okay.
So it's an interesting and challenging research direction. I'm very excited about.
What were the results of that paper? How far did you get with it?
So what we saw is some of the results that I mentioned before. So we saw that if you take a state-of-the-art computer vision model, image classification model, and train it on the most standard data, you will see stuff appearing that are not expected. For example, you will see that the model considers, if you show it a picture of Barack Obama, it will classify it as basketball. And we have real examples like that in the paper. And if you show it a picture of the president of China, it would classify it as ping pong. And this can be shocking, but it's just some biases that are present in the data. In fact, there is something very interesting that we show that actually we found out, which is we thought that this was due to the imbalance in the class basketball, for example. We thought that the class basketball only contained pictures with mostly black people. But when
I've assumed this whole time that that's what you're that was what you were saying.
Actually, that's not what happened. So
really,
yeah. So we computed the statistics, and what we found out is that the class basketball basically contains as many pictures with white people as pictures with black people. So if you take a picture, the probability that there is white people is roughly the same as the probability that you see a black person in it. But what happened actually is that if
maybe black people are much more underrepresented in your data center, so they're more uniquely associated with the basketball.
Absolutely. So it's a mutual information problem. So if you look at just the first order observations, then you may not really see what's happening. But if you look at the problem more broadly, then you see that it's exactly what you said. So that even in the data set, black people are more uniquely associated with the class basketball, which is a bit problematic because, again, it says something about how the data set was collected. And I'm sure that the people who collected the data set, they did put at the time a lot of care to make everything as correct as possible. But still, you can see the type of biases that can arise from the data set. Yeah.
And so we're talking about algorithms that can learn to identify these issues. And you mentioned the ping pong and basketball examples. In that research, did your algorithm, were these kind of handpicked examples, or did your supervisory algorithm find these examples within the first model?
Yeah. It's really not handpicked. Actually, I gave these examples because it's racial biases and people know what it means. But we found other things. For example, for the class traffic light, we found out that the model, whenever there is in an image a blue sky with a bar, some black bar in it, the model will always predict traffic light, just because doesn't matter whether there is traffic light or not. Just because in most pictures with traffic light, you see this metal, this iron bar in a blue sky or something. So it's really it's really a lot of different biases. But I just gave these two as examples because people can relate with it and know exactly what that means.
Can you envision or at least I'm envisioning as you're describing this, maybe some kind of meta annotation process where you initially annotate your data, but then you run and you train a model, and then you kind of apply this algorithm to the model, and it shows you all of these biases, and then you have this meta annotation step where folks are identifying whether these biases are valid or something like that, and using that to retrain your model. Do you envision something like that?
Actually, I will take it one step further. I will remove even the human in the second loop. If things are done properly, ideally what I would like to see is that a model learns from the data in an initial step and itself criticizes itself and says, I should not have learned this and that, and then goes in a second round of learning and be more careful what it learns from which data point, etc., and iteratively produces a final model that is at least less biased, because you never can have a model that is completely free from all biases. That's just not possible. But you can mitigate it, and in my opinion, that's something that we definitely can do.
This question may be getting further ahead of where you are with this research, but given this any of these examples really, but this example of the blue sky and the bar and the traffic light, the way we train these examples, or these models rather, what do you envision the mechanism being inside that training loop that allows the model to even know what the thing is that it's supposed to be paying attention to?
So there are two things here. The first is the the learning rule that we're using. So currently, most of these models are trained in a completely supervised way. So we say, hey, this is an image of a traffic light, and then the model kind of learn to figure out these things. So I think that we should reduce the supervision. That's one thing. And reducing the supervision, having a learning algorithm that needs less supervision will make definitely the algorithm more robust, because it will have access to much more data, which is unsupervised, and the labeling process itself is very noisy in general. So the model may be exposed to less noise, and it may less overfit. So if the model is able to leverage more of the unsupervised data, it may end up less overfitting. So that's one thing. The second thing is that the objective functions that the model is optimizing should be designed in a way that makes the model avoid learning some biases, and that's where that's also one change that needs to happen in the way we supervise the model. So I just give you an example. So right now, the way we train if you take any state-of-the-art ImageNet model, it was trained in examples that have pictures and label, and the model has no idea how the labels are related to each other. It end up somehow figuring it out, and I should not even say figuring it out, but it ended up producing representations. Yes, representations where cats are close to dogs, etc. But it's not really the case. So your model can make completely stupid mistakes. So if a cat is misclassified as a dog, it's a wrong decision, but it's still fine, because semantically we know that they're closer to each other than a cat being misclassified as a plane, for example. And so far we have not managed to train the models to really take into account this decision in order to improve their accuracy and the type of errors they take. So there are a lot of attempts in the literature, but in my opinion, it has not been very convincing. So there is a lot of things to explore in these directions.
Yeah, it sounds like there's definitely a lot to explore, and furthermore, the kind of the direction that you're proposing is is dramatic too strong? A dramatic shift from kind of the way we train these models today.
Well, at some point, we just need to change paradigms, and that's how research works. I'm not claiming that what I'm saying is the right thing to do. I mean, it's probably not, but I see that I observe that we're reaching the limits of most of the learning algorithms and the models that we're currently using can offer. And probably what will take us to the next level is not in the box in which we're thinking right now. So we should probably take a step back and look at the very principles of the learning algorithms that we're using and think them in a way that can take us to the next level.
Awesome. Well, I think that sounds like a good place to wrap up. Mustafa, thank you so much for taking the time to chat with us. Any final words that you'd like to add?
So thank you very much for inviting me. It has been a pleasure to discuss with you. I just would like to mention a last thing, which is there is a lot of research currently in the area of bias and fairness and all of these very interesting and fascinating topics. But there is also one thing that, in my opinion, is a bit overlooked in the community, which is fairness and bias is not only in the models that we design or the data sets the models learn from. It starts with the problems that we consider. If we start by considering problems that are important for a specific population in the world and just focus on solving these type of problems, the end result is the data sets that we'll be using and the models that we'll be learning from these data sets will obviously be biased. So I think as a community, we should also open ourselves to consider problems that are of interest at the global level. And I will just give you an example to conclude. We are there is definitely, definitely an exciting direction, all the work happening in self-driving cars, etc. And a lot of resources is being poured into this, and it's important for humanity in general, I think. But right now, this is important for a very, very tiny percentage of the population of this planet. And there are challenges out there where, as a community, we could have a huge impact, but we are still overlooking, and we should open ourselves to that. And that I just would like to conclude by mentioning this. But thank you very much for inviting me to this podcast. I was very happy to discuss with you.
Absolutely. Thank you so much.
Thank you.
All right, everyone, that's our show for today. Remember, we want to hear from you on AI in the home and in our personal lives. Head on over to TWiMLAI.com/myai to share your thoughts. For more information on Mustafa or any of the topics covered in this episode, head on over to TWiMLAI.com/talk/108. Thanks for listening, and catch you next time.